This is going to be the toughest day of your culinary lives. This is going to test your mental, physical, and culinary creativity from here on.
It can only make it harder.
We're about to take this adventure to a whole new level. Protect your food! Do not do this at home, children.
If that's not extreme, I don't know what is.
Has this ever happened to you? Imagine that you are at a party, and you slice into a beautifully decorated rectangular cake, only to realize that not everyone will get a fair share of this wonderful frosting. After pondering this for a few minutes, you finally realize what must be done. You must somehow maximize the frosted area of the cake in order to get as much frosting as possible. Your mission, should you choose to accept it, is to apply optimization concepts from calculus to make the ideal rectangular cake with as much icing as humanly possible. Today, we are going to do just that, and attempt to maximize the amount of icing we can put on a rectangular cake while keeping a constant volume. First, we know that the volume is 48 pi cubic inches because our cake mix will make enough batter to fill two 8-inch round pans, which gives us a total volume of 48 pi, and this will hold true for all cakes made with this mix. Next, we need our surface area equation for the rectangular cake, which will be the sum of the side areas of all but the bottom of the cake, since we are measuring only the frosted sides. Finally, our last piece of information is that the ratio of the sides of the pan will be approximately 0.7, based on the fact that our three rectangular pans have approximately that ratio. Using these equations, we will isolate two of the three variables, leaving the surface area equation in terms of length. Our final surface area equation is 0.7 L squared plus 960 pi over 7L plus 96 pi over L squared. We then take the derivative of that equation. In order to find the maximum surface area, we set this equation equal to 0, since the maximum value of an equation can be found where its derivative equals 0. We then solve for the variable L and find a length of approximately 7.165 inches. To find the other two dimensions, width and height, we use our other two equations from the beginning of the problem, plugging in 7.165 per length. By doing this, we find a height of approximately 4.196 inches and a width of about 5.016 inches. There is one apparent problem with these measurements. Our pan sizes are 9.5 by 13.5, 9 by 13, and 8 by 11.5, all with a depth of only 2 inches. However, we can make a cake of approximately our calculated dimensions by making an 8 by 11.5 by 2 cake and cutting it in half, then stacking the halves in a 2-layer cake. Of course, our dimensions will not be exact since we are limited by pan size, but the dimensions will be reasonably close. Now, it's time to bake the cake. Finally, our cake has cooled and it's time to see just how much frosting we can get on this cake. As it turns out, we maximized our surface area so much that it looked like the can of chocolate icing would not be enough to cover the whole cake. But as you can see, Megan managed to stretch it far enough to make it around the edges. Then, we decorated the cake with our calculations and headed to the cast party, where everyone had their maximum share of frosting on every slice.